faithfully delivering value, exploring the world's best books. Hello, this is Sally's Book Talk. Today, I'll interpret the book Through the Parallel Universes for you. When we gaze at the stars, we often have deep questions about the universe in our hearts. Like, does our universe have an edge? What's beyond it? Could it be other universes? Are parallel universes just stuff from sci-fi? Could I find an exact copy of myself out there? Hmm. Today, I'll tell you about Through the Parallel Universes, a book that'll blow your mind all at once. It shows that parallel universes aren't fantasy. They might actually be real. This involves cutting-edge research in theoretical physics on parallel universe theory, borrowed by countless directors in sci-fi movies like Coherence and The Hitchhiker's Guide to the Galaxy. The book, Through the Parallel Universes, helps us grasp those mind-bending sci-fi works. Of course, it also brings us closer to the universe's ultimate mysteries. The author is Max Tegmark, a tenured physics professor at MIT. Some say he's among the most original physicists today, closest to Richard Feynman. In parallel universe research, he's a world-class authority. The book has about 450,000 words, and I'll break it down for you in two main parts. Part one, what's the scientific basis of parallel universes? Part two, what's the world of parallel universes like? Next, I'll start with part one, the scientific basis of parallel universes, cosmic inflation theory. Inflation meaning expansion. This theory explains the origin of the universe. Now, let's talk about how scientists explained the universe before the Big Bang Theory. We all know it as the Big Bang. Scientists say that 13.7 billion years ago, the universe began with a big bang, then slowly expanded and cooled, forming our vast universe today. There's plenty of evidence to back this up, but it has two flaws. First, it can't explain. If it were just a big explosion, there should be a heat source. Then the cooling should have made areas closer to the explosion hotter, and farther away it would naturally be colder. But scientists measured temperatures across the universe and found they're almost identical everywhere. If there really was an explosion, it must have been a big bang happening simultaneously at countless points. But how could so many big bangs happen perfectly simultaneously everywhere in the universe? The Big Bang Theory can't explain this. Another issue, scientists calculated that if the universe's matter were slightly denser, it would undergo a big crunch. Because gravity between matter would be stronger, pulling everything together, causing the universe to contract and crush, heading towards destruction. And if the universe's matter were sparser, it would undergo a big freeze, meaning matter spreads farther apart, gravity weakens, so everything scatters away, and the universe also ends. But in reality, neither of these scenarios happened. Our universe is just right. Not too dense, not too sparse, always in a critical state. Why is that? The Big Bang can't explain it either. Later, scientists found a model that perfectly solves these problems. Cosmic inflation, what we're discussing today. This model suggests that long ago, there was a tiny, uniform blob of matter with extremely high and unchanging density. If 1 gram of this matter expands to twice its volume, it becomes 2 grams. This undilutable matter takes the same amount of time to double in size each time it expands. So 1 becomes 2, 2 becomes 4, 4 becomes 8, like infinite duplication. If this process continued forever, it would be an eternal explosion. But if all matter were constantly duplicating nonstop, how did so much stable matter form in our universe? So scientists proposed that during each duplication, some matter stops inflating and decays into ordinary, non-inflationary matter. For example, inflation isn't 1 becoming 2, but 1 becoming 3, 3 becoming 9, 9 becoming 27. But during each inflation, 1/3 of the matter stops decaying, becoming ordinary matter. The remaining slowly forms galaxies, stars, etc., like smoking a cigarette. 1/3 becomes ash in the ashtray, while the rest continues inflating and splitting. In other words, inflation did indeed end in some places. In these regions where inflation ended, galaxies begin to form within a specific area. If inflation ends and becomes a normal region, the matter here initiates the traditional Big Bang. After it transforms into a hot nuclear fusion reactor, then gradually cools down, forming atoms, galaxies, and so on. This process begins, and this cosmic inflation model solves the problems we mentioned earlier. Why is the temperature almost identical in distant regions of the universe? That's because they share a common origin. They all stem from that initial small blob of inflationary matter doubling repeatedly. The cosmic inflation model provides reasonable explanations for many cosmic problems, so it's increasingly accepted by mainstream scientists. What we just covered is part one, the theoretical foundation of parallel universes, cosmic inflation. A very natural corollary of this theory is that our 13.7 billion year old universe isn't the sole product of the cosmic inflation process. It's just a clump of ash left behind where inflation ceased in one region. Throughout the eternal inflation process, countless other regions like ours become clumps of non-inflating ash, forming similar universes. We just haven't observed them yet. So, it seems parallel universes aren't such a wild idea after all. It's simply a natural corollary of cosmic inflation theory. The universe we currently know is only a small, observable fraction of the entire cosmos. Beyond this part, the whole universe has infinitely vast, unobserved space. All right, next, let's lift the veil on parallel universes and open a huge mental exploration to see what the author reveals about them. You pay attention. From here, we need to distinguish two concepts: multiverse and parallel universes. The author states there are four levels of the universe. Each level contains numerous parallel universes. One level is like a floor, and a parallel universe is like a room on that floor. First, let's start with the easiest scenario. The first level, multiverse, where there's another you in a distant place, equivalent to the first floor. It contains all the first level parallel universes, including the one where our Earth is located. Generally, we can call this room our universe. It's a huge spherical region with a radius of 13.7 billion light years, and Earth is roughly at its center. And because the Milky Way galaxy we're in is itself near the center of this sphere, there isn't much controversy about the first level multiverse. They're essentially the products of other regions where inflation stopped. These universes share similarities with ours. The physical constants are identical. For example, gravitational constants and such. Oh, their universes also have atoms and molecules, but the arrangement of particles might be different. Say, in our universe, 10,000 atoms form a speck of dust, but in that universe, 10,000 atoms might rearrange to form something else. Of course, it's possible that the arrangement of those 10,000 atoms is the same. Similarly, in other universes, there could be a person whose atoms are arranged exactly like yours. Scientists can calculate this mathematically, but oh, it's an astronomical number. Beyond 10 to the power of 10 to the 29th meters from our universe, there's another you living in their galaxy. If you don't mind the distance, go ahead and search. You'll always find a universe where you never get a parking ticket in your entire life. You just have a different name there, and in that place, you won $1 billion lottery. Not just identical, you can even find a universe exactly like ours. The number of possible arrangements of matter, though vast, is finite. There are 10 to the power of 10 to the 118th possible arrangements. Oh dear. In other words, if you want to find two identical universes, you need to travel in a straight line across 10 to the power of 10 to the 118 universe diameters to reach one. The first universe identical to ours. Oh, wow. If the eternal inflation process created a vast space containing infinitely many first level parallel universes, then it contains all possibilities. That's the imaginative space the first level multiverse offers us. Hmm. Do you already think this concept is mind blowing? But wait, there's more. Then the author serves us an even grander vision. On this grand vision, what we discussed earlier is just a sesame seed on that grand picture. This is the second level multiverse, a place humanity can never reach. A fundamental feature of these universes is that their physical laws are generally similar to ours, but their fundamental physical constants differ. This might still sound too abstract. Let's roughly sketch what this second level multiverse looks like. Imagine in winter, standing under a tree, seeing bare branches dividing the sky into patches, with cosmic branches beyond. Each divided small patch of sky represents the product of inflation ending the first level multiverse. That small sky patch is like a pocket holding countless universes like ours. Our universe is as tiny as a balloon floating across that small sky patch. When you gather all those small sky patches between branches, all first level multiverses, that totality forms the second level multiverse. How dare scientists claim this? How can they say there's a second level multiverse in unobservable places? Because scientists discovered that seemingly empty space around us isn't empty. Space is a medium with multiple states. Scientists call these states phases, like photophases, analogous to water's three phases: ice, water, steam. But space has vastly more phases than water. Space has 10 to the power of 500 phases. That's a 1 followed by 500 zeros. We exist in just one phase, each space phase corresponding to a small sky patch between branches. A first level multiverse is filled with one phase, while other spaces don't share our phase. In the second level multiverse contains spaces with all possible phases. First and second level multiverses we discussed sound like vastly expanding the space we know. So our universe isn't everything. It's just like room 702 in a building. Stepping out, there are many more rooms, many more floors. Now, the third level multiverse doesn't expand in that direction. It's not about distance, but about the reality we experience beginning to split. Many know a fascinating thought experiment called Schrodinger's cat. It involves placing a cat, a glass vial of poison gas, and radioactive material in a sealed box. But when a monitor detects radioactive decay, it shatters the vial, killing the cat. If you open the lid to look, the cat is either alive or dead. If you don't open it, the cat exists in a superposition of both alive and dead states. According to quantum theory, after an event occurs, all possible outcomes form their own universes. That's the third level parallel universe. How to grasp such an insane idea? Say you're deciding between Northeastern or Sichuan cuisine for lunch. After choosing, your consciousness splits into two versions simultaneously existing. Existential duality. Both feel completely real, utterly unaware of each other. Each existing possibility at any moment births a new world. Parallel universe division continues endlessly beyond counting. Their numbers started multiplying from the Big Bang, vast as oceans, exceeding all sand grains in the universe. So where is this third level multiverse comprising infinite parallel universes in Hilbert space? But we won't elaborate today due to time constraints. Just know it's an abstract space with infinite dimensions, not three. Some might object, I don't feel myself constantly splitting into multiple versions. But the author counters, you also don't feel yourself orbiting the sun at 30 kilometers per second, yet that's your reality. So don't let physical senses limit your imagination. You perceive only one universe because quantum mechanics has a confidentiality mechanism. Superposition only occurs when position remains unknown. If the secret leaks, all superposition effects instantly collapse. After observation, it's either or, here or there. So, how does this observation leakage process happen? Does it require human eyes? Does it need a camera? Neither. It just needs a single photon hitting it. Imagine a pitch black room where you see nothing. There's a mirror in superposition. You're unsure where it is. Suddenly, a photon enters and flies straight at the mirror, bounces off it. You wait on the photon's path. When it hits your eye, you see the mirror. Oh, it's here. Actually, when the photon hits the superpositioned mirror, it collides with air molecules, spreading the location like gossip. Seeing the mirror via photon reflection is irrelevant to the leakage process because information leaks the instant the photon hits. Observation in quantum mechanics isn't conscious watching, it's just information exchange. Why don't we see superposition in macroscopic objects like bowling balls? Because molecules hitting it collide with air molecules, rapidly spreading its location. Like a secret spreading, one tells 10, 10 tell 100, so it's no longer secret. That concludes the third level multiverse. Some might confuse it with the first level. In first level multiverse, universes are far apart in linear distance. In this universe, I might miss a date, ending up breaking up. But in another parallel universe, I go on the date, even marry and have kids. Third level is different. It's me now hesitating whether to go on that date. At one moment, I flip a mental coin and decide to go. And in Hilbert space, reality splits into different storylines. One version of me went, another didn't. You could say the first level multiverse is spatially distant, while the third level begins splitting from a single moment. If by now you think this is already crazy and mind-bending enough, next, the author presents his ultimate idea, his most significant personal viewpoint, the existence of the fourth level multiverse. The universe is a grand book written in mathematics. The author says, through his lens, the universe isn't material, not physical, but mathematical. In daily life, we observe mathematics everywhere. For example, a basketball thrown forward follows a parabolic arc to the ground. If you spray water from a hose, it too forms a parabola. What falls is irrelevant. What matters is the identical mathematical model. Similarly, gravity causes a comet orbiting a star to trace an elliptical path. In fact, ellipses abound in the cosmos. A star orbiting a black hole, Sirius B circling Sirius A, all following elliptical trajectories. Everything in our universe can be abstracted into pure mathematics. The author argues reality isn't merely described by math. It is math. For instance, objects like basketballs, chess pieces, goats, or lamps are human-defined bundles, convenient packages for matter. If we discard these bundles and describe the abstract patterns governing them, we arrive at mathematical structure. 1 plus 1 equals 2 embodies mathematical structure, representable through any bundle. 1 apple plus 1 apple equals 2 apples. 1 basketball plus 1 basketball equals 2 basketballs, etc. For every significant human concept, we create new bundles. But the theory of everything scientists seek has no bundles. It's pure mathematical structure. To the author, the universe's deepest reality is mathematical structure, not molecules, atoms, or quarks. These are just differently sized bundles. If we dig to the root, what is the universe truly composed of? Is it some indivisible particle or substance? The authoritative counterpoint disagrees. He believes the universe's ultimate reality is mathematical structure, a formula we haven't written yet. One mathematical structure governs the entire cosmos, giving rise to atoms, molecules, matter, and stars. Thus, Tegmark's fourth level multiverse, the ultimate layer, is the mathematical universe where math reigns supreme. And in fact, each mathematical structure corresponds to a multiverse with different structures creating different multiverses. And to help you grasp this, I'll use an analogy. Suppose Einstein's E equals mc squared exists, but the super formula ruling all multiverses is E equals mc superscript n, where m is an integer. This formula should explain all fundamental laws of our universe. like why the universe expanded so rapidly during the Big Bang. Why are electrons like this? Atoms like that? With this formula, varying initial conditions, like physical parameters, yield different universes. Like a martial arts manual, I master boxing with it. You develop shadowless kicks. Same principles, different outcomes. One manual creates diverse fighters. One mathematical structure spawns diverse universes. To summarize, the author presents four distinct multiverse levels. Their differences. First level, regions so distant light hasn't reached us yet. Second level, separated by eternal cosmic inflation, branches dividing skies forever unreachable. Third level, quantum isolation, constantly splitting in Hilbert space, unaware and non-communicating. Fourth level, mathematics as ultimate existence. Among these four levels, the higher ones are more macroscopic, abstract, and universal, while the lower ones are more specific, down to our own universe. Finally, I want to tell you, don't think the multiverse itself is a theory, it's part of certain theories. For example, inflation theory provides some reasonable predictions. Because inflation theory itself has gradually been accepted by mainstream scientists and is widely discussed, moreover, it's very useful and can solve many cosmological problems. Therefore, the multiverse inferred from inflation theory is a crucial one among current human explanations of the universe and can't be ignored. But what? What? It's not that inflation theory and the multiverse concept are necessarily the ultimate truth. However, scientists are currently pursuing a unified theory of everything, and the multiverse idea is a strong attempt at it. It still awaits further development and testing by future folks. Let's wait and see. Perhaps one day, breakthrough research on the multiverse could completely renew our understanding of the whole cosmos. When we look up at the stars, we become more fascinated and cherish the universe we live in. All right, through the parallel universes, that's the end of the interpretation for this book. Listening notes are below the audio. See you tomorrow.